Next chapter, next subsection of this chapter, that is on probability. Okay, so now we'll learn how to define probability of an event. We have already seen what's the subspace, what are events, what are simple events and all, mutually exclusive events. Now we'll see the calculating the probability of an event. Okay, so first let us start with definitions. So just for the sake of simplicity in this course, we will be considering only experiments whose sample space is a finite set. Okay, or a sample space consists of finite number of elements. Like for example, in experiment which will involve infinite number of elements is like if in case you have to pick an real number. Okay, we had discussed this earlier on in the course in the introductory classes that the set of real numbers is an infinite set. Okay, so it's an infinite set. Even the set of natural numbers is an infinite set. So picking an arbitrary natural number, if you talk of that experiment, then it will be an infinite set. Okay, so such kind of large sets or infinite sets we won't be considering. We'll be considering only sets which are finite, of whose total number of elements in the sample space are known to us. Okay, this is just done for the sake of simplicity. Also, if you want to consider infinitely many elements, these definitions which I am giving you right now, they won't be working. So we have to redefine the things in a different way. Okay, that becomes a different theory. We won't be getting involved with that. Okay. Yeah. So let us define this thing as the likelihood of occurrence of an event resulting from such a statistical experiment in which the sample space is finite is evaluated by the set of real numbers called weights or probabilities. Okay. So the outcome of this experiment will be assigning it a weight which will be called a probability. Okay. So the possibility of something happening will be giving it a weight, and that weight will be calling as a probability. So that value will be something between 0 and 1 which will decide according to some rules which we will be giving after some time. Okay. So to every point in the sample space we assign a probability such that the sum of all the probabilities is 1. Okay. Now one important thing here is we can do this thing only because we have finitely many people in our sample space. Okay. So since there are finitely many people there, we can assign each one of them as some probability. If we are given infinitely many people in the sample space, this activity may not make sense over there. Okay, only because we have finitely many elements, this thing can be done. So just keep this as a note over there in your margin or somewhere that the third point can be done only because we have a finitely many people in the set. Okay, let's move on. Finish writing? Right first. Okay, done. Let's go on. So now this is the logic which we will be following while assigning some weights to the sample points. Okay. I had only told you that we are going to assign to each sample point a weight between 0 to 1. Okay. So if a certain sample point is more likely to occur when the experiment is conducted, then the probability should be closer to 1. So in other words, if the point is more likely to occur, the event is more likely to occur, the higher will be its probability. Okay. And if a certain sample point is less likely to occur, then when the experiment is conducted, then the probability should be closer to 1. Okay. Let's note this down. It's really curious why most of you are sitting in this corner of the class. And the board is there like that. Like almost half the class is sitting in this just 30% area, no? Is it because of the AC or something? What does good friends have to be sitting so close to each other? Like, there are so good friends, huh? Okay, I'll just read to the slides which you all missed. Those who can read, just going backwards. So this is what we had discussed. Each sample point in the sample space will be assigning some value between 0 to 1. Okay? That value will be called as the probability of that sample point. Okay? So if a sample point is more likely to occur when the experiment is conducted, then the value will be closer to 1. Otherwise, it will be given a value closer to 0. Okay? Like for example, a simple thing I'll tell you all. If let us say a football match is going on, okay, national level football matches are going on. So if Indian football team is playing against Argentina or Brazil, what do you think are the chances of winning for India? Huh? Just say for example something happens and India decides to play a match against Argentina or Brazil. What are the chances of the game, India winning the game? Huh? How much? Is it more? Is it? Huh? 1%? Okay, so he says there is a 1% chance of India winning the match, right? So in other words, we know that India has a very less chance of winning this match against Argentina, even if Argentina sends their B or C level teams, right? Agreed, no? Even their B or C level teams will be better than the Indian main team. Okay? So in this case, what probability value will assign to this particular match of India winning the game? We'll keep it very close to 0, right? Yes. Correct, no? Okay? So in the other words now, in another example, if India is playing a match against Bangladesh, what do you think will be the chances? Huh? Yeah, we're playing football, not cricket. India versus Bangladesh, you think? How much you think? We'll have to give them 50-50%, right? Okay? Because it can go any way, we don't know. This depends on the day, on what they're playing and what is the mood of the players that day. Right? Because Bangladesh also is a very competent team if you compare it with the Indian team. Okay? Actually, I gave you all the example of football. I can't think of a team which is worse than India. Are you sure? 100%? No, because I don't know. Because I even know that teams like Syria and Yemen, which are fighting a civil war, are better than India. They can afford to put a better team there. Oh, okay. Now for the other way, we'll have to go to cricket as an example. So if India decides to play a game against teams like USA or what else is there? Canada or something like that. Okay, what are the chances of India winning now? So in such situations, the chances of India winning are much higher, right? Okay, so that time we can assign a probability like 99, 0.99 or 0.98 or something like that. Okay. Even if India is playing a cricket match against Australia, no, we can give 0.7 to India over there, or 0.6 in the worst case scenario. Okay. So what we realize here is, if the chance is more, then we'll give it a higher probability. If the chance is less, we'll give it a lower probability. Okay. Yeah. So if the point does not lie in the sample space, then we assign it a probability of 0. Now this example, I'll have to give you something different here. It's like when you're playing the game of cricket, the probability of scoring 9 runs on a given ball. Can that happen? No, right? We had seen that the maximum that can happen on one ball is 7. Okay. So the probability of getting 9 runs on a given ball, that's actually a point outside the sample space. So it should be having probability 0. Okay. Let's go on. Yeah, if all the sample points are equally likely to occur, then we assign them the equal probability. Okay. So now when you're playing a sport, it is never equal, anything can happen, right? But in some simple experiments which you conduct, like tossing a coin, we know there's a 50% chance of getting a head, 50% chance of getting a tail, right? So in that case, we assign the probabilities as half for head, half for tail, 0.5 for head, 0.5 for tail. Another thing is like rolling a die. If the die is a fair die, then we know it can get a, what do you call that, probabilities, like each of the points values can come equally likely, right? So in that case, we'll be giving it 1 by 6, 1 by 6, 1 by 6 for each of the 6 points. Okay. One thing what I have to explain here is, in case we are tossing a fair coin, both heads and tails are equally likely to occur. So in this case, you assign the probability as half for each of them. One important thing here is, what do you mean by a fair coin? What is a fair coin? And what other coins you get? You get coins with some other option over there other than heads and tails. No. What do you mean by fair coin? Anybody? Another word which we use here is unbiased. I think so I've written it down somewhere. Okay. So fair coin or an unbiased coin means that there is this thing, 50-50 chance of any one of those two events happening. Okay. What can be a biased coin? Means the negative of the statement will be the coin is biased or the coin is not fair. So what do you mean by this? When you toss the coin, there is a more chance of one of the two sides coming. Okay, it's not a 50-50 thing. Like to give you an example, this 1 rupee, 2 rupee coins, they are not designed for this activity of tossing, right? So especially the 2 rupee coins, if you noticed, every few years they change the design on the back side. Okay, like if there's some special event, some anniversary or something is there, then that person's or that buildings or whatever or that organization's logo is put on the back side of the coin. Okay, like when if there's any temple, this thing, or there's some 150 years of some thing or something like that, 75 years, 60 years or something, that organization's logo is put on the back side of the coin. Even for 5 rupee coins they do that. Okay. So yeah, so since the design is changed, you know that design is put in that way over there, what happens is, usually it happens that the back side of the coin is heavier than the front side. So when you toss this coin, the probability is very high that the back side will go down and the top side will remain on top. Okay. So these coins are different from the coins which they use for cricket games or some football games or something when they have to toss. Those coins are completely different and they're designed for that activity so that the heads and tails remain unbiased. So whenever the coin is tossed, it can come a head or tail, we never know. Okay. But your this regular 2 rupee coins or something, they are to a certain extent biased because of their weight. Okay, this is simple physics that if the weight is higher on one side, it will fall that side down. Okay. Yeah, so that's the thing about fair coins. So fair coins means there's 50-50 chance of either of the two sides coming. Okay, same thing happens even for rolling a die. All 6, rolling a fair die again, all 6 sides are equally likely to be assigned the probability 1 by, equally likely to appear, so they assign the probability 1 by 6. Again I'm saying a fair die here, so all the 6 numbers have an equal chance. Okay. One thing about fair dice is, if you all have noticed a good quality die, what they do is, just to tell you all, there are 6 sides of the die, right? So they don't actually paint on top of them, because if they paint on top of them directly, the paint will make it heavier on one side, especially the side with 6 is there. That side will become heavy because there are 6 drops of ink over there. So the weight will kind of be more on that side, and it will obviously tip on that side downwards. Okay, so it will be very less likely that 6 will come on top. Okay, because 6 will always go on the side or down because the weight is heavier that side. So what they do is to maintain the weight equal on all sides, they drill a hole on all the sides according to the number of things they want to fill, and then they use a paint whose actual density is same as the material which is being used. Okay, so if your die is of plastic, they'll be using a plastic paint whose weight is same as the plastic, the density is same. So this ensures that even though there's 6 dots printed over there, those dots are filled with the same weight as the original weight. So the weight is balanced on all sides. Okay, yeah. So this is just some extra general knowledge here. Let's go ahead. So now let us define the probability of an event. So the probability of an event A is the sum of the weights of all sample points in A. Okay, so each sample point has been assigned some weight. Okay, the event is made up of a collection of sample points. Okay, so the probability of event is nothing but the sum of each individual weights in the set. Okay, so now, so the probability of an event will have to be something between 0 and 1 again, because it's made up of values which are lying between 0 and 1. Okay, yeah, and the sum of those values which were used, the sum of the values which are used to add up and you getting the value of probability of A, that sum was equal to 1. Remember, no, the definition which I had given you some time back, I said the sum of all the weights should be equal to 1, right? So if you are taking all the weights, then only the probability of A will be, if you are taking all the points, then only probability of A will become 1. That's what I mentioned here, probability of S is equal to 1. So basically you are taking the full set. Otherwise, if you are not taking every one, the probability has to be lying somewhere between 0 and 1. If it is 0, that means it's an empty set. Okay, in other words, this is an impossible event. We had spoken of this earlier, right? So an impossible event will have probability 0 and the whole event will have probability 1. Okay, so going further, if A1, A2, A3 up till A whatever is a sequence of mutually exclusive events, then probability of A1 union A2 union A3 and so on will be equal to the sum of the individual probabilities. Okay, but one important thing here is that A1, A2, A3 are mutually exclusive. Okay, what do you mean by mutually exclusive? They don't have any common intersection. Okay, just keep this in mind. Now, mutually exclusive means they have no common intersection. You know, intersection is empty between them. Okay, you finish writing? Oh, write first. Finished? Let's go ahead then. Okay, so if we talk in a completely finite setup, if an experiment can result in any one of the n different equally likely outcomes. So if you have an experiment where there are n possible outcomes, all of them are equally likely, like in case of what do you call that, rolling a die where there are 6 possible outcomes, all of them are equally likely. Okay, so we're talking of that kind of thing where there are equal likely cases. So in general, if there are n instead of just 6, and if exactly n of these outcomes correspond to an event A, then the probability of event A is nothing but small n divided by capital N. Okay, let's see this with the help of an example. Let A be the, you're first writing this? Right, first I'll just give you an example on this. Done? So let me give you an example on this. Right fast. Done? Okay, like for example, rolling a die. Just take this an example over there. Rolling a pair die S6. S6 equally likely. Outcomes. Okay, so n is equal to 6 over here in this case. Okay. Let A be the set of event that the outcome is an okay. So how many people are there in A? How many even numbers are there in A? 3, right? The original set is 0, 1, not 0. Only 1, 2, 3, 4, 5, 6, right? So out of the evens are 2, 4 and 6. So this is equal to 3. Okay. So hence the probability of A will be what? It will be small n, that is equal to 3 divided by 6, that is equal to 1 by 2. Okay. Another thing we can try, B is the event that the outcome is a multiple of, okay, so how many numbers over here are multiples of 3? Only two of them, right? Which are they? That is 3 and 6. So what should be the probability in this case? 2 by 6, right? That will be n of b will be, there are two outcomes which are multiples of 3, that is 3 and 6. So probability of b over here will become 2 by 6, that is equal to 1 by 3. Okay, clear? Okay, so let's go back to the slides. Okay, so that was one definition of an probability. The another way of defining probability is using relative frequency. Okay, so if an experiment is conducted a large number of times, then the probability of an event A will be the fraction of number of times A occurred by the number of times the experiment was conducted. Okay, so now in certain things we don't know what is the straightforward probability. Like for example, in case of rolling a die, we saw that there are 6 possibilities. So anything comes next will be one of the 6, right? That's what we had said. But sometimes what happens is, like when you're playing a game of something, cricket or something, between two teams, right? And as we'll assume that the same team is playing under the same conditions, so there's no change of the pitch or something like that, or the players are changing or something like that, right? So if the same two teams are playing against each other, after they play like 10-20 matches, you realize that one particular team is better than the other, right? Okay, or maybe you can say then they are almost equal. Like for example, 20 matches were played between team A and team B, out of which 15 games were won by team A and 5 games were won by team B, right? So what can you say over here? Team A has a 75% chance of winning the game, right? No? Okay, and the other team has only a 25% chance of winning the game. So probability of team A winning will be 0.75 and probability of team B winning will be 0.25. Clear? Okay, so this is called as a relative frequency definition of probability. Okay, where we perform the experiment again and again, right? And based on that, we decide what should be the probability of A and probability of B. Okay, so the probability of event A will be the fraction of the number of times A occurred by the number of times the experiment was conducted. Wait. Who is writing this? Right. Finished? Wait, I'll write this example and go back. So an example what I'm giving of relative frequency is this. Team A and team B play 20 games each other Team A and Team B play 20 games against each other, or under the same conditions. Okay, Team A and Team B. Yeah, Team A. Okay. So in such a situation, probability of A winning the game will be 15, the games which they won, divided by total number of games they played, right? And same way, probability of B wins Okay, so this is, as we know, 0.75 and this is 0. Observe that the addition of both of them gives you 1. Okay, done? Yeah, those of you who didn't copy now can copy. Okay, so moving on. So let us go now to the properties or additive rules of the probability. Yeah, I forgot to give. She is in a hurry. What happened here now? Okay, there's some problem with this animation. Okay, so if A and B are two events, then the probability of A union B happening will be probability of A plus probability of B minus probability of A union B. Okay. Okay, so what is my probability of A union B? It's the probability of A occurring or B occurring, right? So union refers to or. Okay, so just keep that in mind. Whenever you have or, you have to do union over here. So next, if A and B are two mutually exclusive events, then probability of A union B will be equal to probability of A plus probability of B. Right, so what is missing here is the intersection term, because if the events are mutually exclusive, the intersection is empty. right? No, if the events are mutually exclusive, then the intersection is empty, and if the intersection is empty, then the probability of that empty set will become 0. So that's how this 1.1 comes out of 1. Okay. And same way, instead of 2, if you have many of them, n of them, then the probability of A1 union A2 union A3 up till An will be sum of probability of A1, probability of A2 up till probability of An. Okay, clear? Let me just prove this, but first I'll write it down, then I'll do the proof. Those colors are visible, not everyone, not too light. No? Okay, so let me write down the proof for this. So we are given probability of A union B is equal to probability of A plus probability of B Okay, so proof for this. So just look at the Venn diagram here. This is A, this is B. Okay, so now I want to count the elements of number of elements in A union B. So how will I count them? How do you count this? First we'll count the elements which are in A. All these elements which are in this set will count, right, in A. Okay, so write them down. That will be number of elements in A. Next, what will count next? We'll count the number of elements which are in B over here. Right? So when you add them up, number of elements in B. But what have I done while doing this? I have counted this region extra. Right now, I counted this red region twice. Once when I was counting A, once when I was counting B. So what should I do? I'll have to remove them from the total. Right? So I'll have to subtract it. Clear to everyone? Okay. So now what I'll do is, this is the total set S, right? Okay. So this all three sides I'll divide by number of elements in S. So number of elements in A union B is equal to number of elements in A number of elements in S Okay, I divided both sides by number of elements in S. Clear? But then, what is this actually? This can be written as number of elements in A upon number of elements in S plus number of elements in B divided by number of elements in S. Okay, but what is this defined as? Number of elements in an event divided by the number of. What happened now? Okay, so what is this now? This is probability of this is defined as the probability of A union B. This is the probability of A. This is the probability of right. This is the result which we have to prove. Right fast. I'll ask now. Easy it is, no? For math students, we have to this only, kind of. So much demand. See, she's saying if I ask this question for 5 marks, she'll write it down. So should I ask this in exam for 5 marks? Huh? Yeah. Nobody is interested for 5 marks. Okay. So moving on. Moving on now, for 1.1 case, if A and B are mutually exclusive, okay, this will imply that A intersection B is empty. Okay, if A and B are mutually exclusive, this means that A intersection B is empty. So this will imply that probability of A intersection B is equal to 0, and hence the result follows that probability of A union B is nothing but the probability of A plus probability of B. In this case, for this case, the Venn diagram changes, by the way. Mutually exclusive means they have no intersection, so this will be A and B. Okay? Why are you wearing a hoodie in the class, by the way? That looks so suspicious. He's from? You're from where? No, he said something else. No. Hello, kept the AC on but the door open. Somebody closed the door over there. And AC gone on mill there. Yeah, close the door. And only one AC is kept. She had gone to close the door. She locked herself out. Okay, let us go back. Finish writing, no? Let him write. Write fast. Huh? Oh. It will come, then why I'll teach if it does not come? I'll ask examples at least based on this. Don't worry if I don't ask the direct question. Well, didn't have proofs for other papers and all? Even linear algebra didn't have proof.
No, we did that. Linear algebra the example given. First but see, sir, when you are getting something. She class quickly
Now I feel my whole career was a lie. Okay, let's go ahead. There's some problem with my slides here. Okay. Okay. Go back. Yeah, okay. One special case of the previous thing what I had written is 1.2 over there. Okay. The follow up of it is 1.3. If A1, A2, A3 up till AN is a partition of a sample space S, then now what is the difference here? Previously it was just mutually exclusive sets, right? Now I'm saying it's a partition. Okay. So what's the difference there? What is the difference in a partition and just mutually exclusive? I'll remember. Partition was what, by the way? Partition was you're dividing the sets. Huh? No, not into two parts. You can divide into many parts. Okay, but the conditions there was that no two people will have anything common between them, and the union of all the members should be equal to the full set, right? So now, if the no two people have anything in common, that means they are mutually exclusive, right? So by the previous property, we'll get the first part over there, that A1 union probability of A1 union up till A1 union A2 up till AN will be equal to the sum. Okay, so this part is clear from the previous thing because they are mutually exclusive. No two people have anything common over there in a partition. What is the second condition for a partition? The union makes up the full set, right? So this union A1 union A2 union AN will be what? It will be equal to S, right? And what is the probability of S? It has to be equal to 1. This is what we had defined earlier on in the today's lecture. Correct? So this just follows from the previous thing. Okay, it's just a special case of the previous property. Okay, now going a little ahead, if you have three events A, B and C, then the probability of A union B union C will be a probability of A plus probability of B plus probability of C. Then you are subtracting these three quantities and adding up the fourth quantity, that's the union of the A intersection B intersection C. Okay? Done? Right first. Right now, why are you looking at her? She's writing for you. Oh, you wrote already. Everyone finished then? Let me just go to the diagram here for this. Okay, so the diagram over here in case of 2, I'll draw a big diagram. A, B, and C. Okay, so notice something here. Let's color this up. So first we'll what we have to do here to count the probability, we have to count the number of elements in the set, right? So first we'll start with counting the elements of A. So we'll count all these elements over here. Okay. Well, broke the well, broke the curtain. You okay? No. Okay, okay. So when we are counting A, we are going to count all this red region over here, right? Now head is not paining, no? Okay. So moving on now. We counted the elements of A. Now let us count the elements of B. Now we'll count the elements of B as all this blue thing. Okay, and we'll count the elements of C as count in yellow. Okay, so now what we have done here while we are counting, we have written, we counted first in red number of elements in A. We'll write in red number of elements in A. Then I have counted in blue the number of elements in B. Then in yellow I have counted the number of elements in C. But what I have done here, I have counted some elements twice, right? Okay, so I'll have to subtract all those people who have counted twice. So can you see here the region between red and blue is common, right? So I'll have to subtract those people here as A intersection B. Clear? Next, we have counted the number of elements in blue and yellow also twice. So we'll count, subtract that out. Number of elements in A intersection C. Then and here we'll have B intersection. Okay, done. We have subtracted all the common regions, but what have we done here while doing this? this particular region, so we first separated the region which is between blue and red, right? So then we separated the region between red and yellow, right? We had so notice here this particular region over here. Okay, I'll have to use the eraser for this. This particular region which I'm highlighting in black over in the center, that got added 3 times and it got separated also 3 times. Okay, so I'll have to add it back over here. Okay. Okay, this black region over here, it was added 3 times and subtracted also 3 times. Okay, so that's why I have to add it back again over here. Okay, clear? Done with the diagram? By the way, in the slides which I'll be sharing, no, whatever I'm doing in the slides only will be visible. This black screen thing will not be visible. For this, you'll have to watch the video or something. Oh, slide on. What happened? I'll be sharing this video with you, this class. Okay. Let's go back then. Finish now. Okay, let's go to the next thing. If A and A complement are complementary, if A and A dash are complementary events, okay, then probability of A plus probability of A complement will be equal to 1. How are you going to prove this, by the way? How can you prove this? What happened? Huh? How can you prove this in 1 line or 2 lines? Using the previous properties only, what I've stated. What are some properties you know about A and A complement in the first place? What are some things, properties and thing you know about A and A complement? A and A complement, they form a partition of a set, right? Right, no? Because the union will give you the full set and intersection is always empty. So in A and A complement are partition of a set, right? So what do we know about the probability of a partition over there? Probability of A union A complement will have to be equal to 1, right? But that also has to be equal to probability of A plus probability of A complement, right? No? That will give you 1. How that follows? That follows from this. It follows from 1.3. Okay, just write down over there, follows from 1.3. Okay, so using A1 as A and A complement as A2, you'll get this. The proof of this statement 3 follows from 1.3. I'm getting a spam call. Let's answer it for fun. Hello.
हेलो गुड मॉर्निंग सर।
हाँ
yes. एस से बात कर रहे हैं सर। एस आपको ऑफर कर रहे हैं इंटरनेशनल वीजा क्रेडिट कार्ड सर विद 100% ऑफर्स एंड फीचर्स। 2 मिनट हो गए तो मैं आपको एक्सप्लेन कर सकती सर।
Okay, you can call later after 12:30.
After 12:30?
Yeah, okay.
12:30. Can you call it?
Oh, sorry, I meant 1:30. 1:30.
Okay, sure sir.
Yeah.
Thank you.
Okay, this was some sensible call. No, in the morning I had got one spam call. What had happened was he had called 2 days back and he had told me that on my card the international usage has been activated. I usually deactivate the international usage on my card and keep, because it's basically it means that the card cannot be used outside India. So no website which is located outside India can use it. Neither some person can do any transaction outside India. So in other words, even the dollar, whatever foreign currency transactions get blocked automatically. Okay, so this guy called me 2 days back in the evening around 4 o'clock or something, and is telling me it has been international usage has been activated on your card. Do you want to deactivate it? I said, yeah. I said, I never activated in the first place. No, he said, accidentally due to something, it has been activated and kept. So you will have to deactivate it. I said, okay, deactivate it. Then he's like, no, you'll have to give me your card details. Then I was like, I don't have my card with me right now. It was in my phone only here. So I said I don't have it now because I found something was fishy here. So I said, you call back again tomorrow. So then next day I checked in the morning early that the thing whether it's active or not. On the app you can check, right, on the bank app. So I checked it's off already. So and he didn't call also again. So today morning when I was got on the bus, I was climbing up now, he called again. So I decided to ask him in detail why he was calling. Then he said the same thing. I told him I have already deactivated it. Then he's like, no, it's active. I said, I just checked on the app, it's deactivated. Don't tell me that. I cut the call. Otherwise, if we continue talking also, they ask more questions. So I thought somebody was calling from there only. So I decided to have fun. Once like this, somebody had called, when I was taking a class, not my phone, they called on one student's phone and they were offering some iPhone. Some phone they were offering, some Vivo or something. There was a company called Vivo, right? Still there. Still there. Yeah, so they were offering some model of that Vivo for a cheaper price. But then I decided to have fun. I had given some problem to write down, and so student was saying that, calling again and again, no. So they gave the phone to me. I put it on a loudspeaker in front of the full class. Then I started bargaining for the phone with them. Then I was like, no, can you give me an iPhone for that price? For some 10,000 something they were offering that Vivo phone. Then I was like, no, I'm ready to pay only 2,000 for this. Can you give it? No. Then she only cut the call out of frustration. Okay, let us continue. Okay, so let us go to the exercises now. You have to finish all the exercises on today. Okay. So a box contains 500 envelopes, of which 75 contain 100 in cash. 150 of them contain $25 in cash, and 275 of them contain $10 in cash. So any envelope can be purchased for $25. What is the sample space for different amounts of money? Okay, write down the question, then we'll solve it. There was this Ambani wedding recently. So for their visitors, they gave some gifts, I heard, like this. But I don't know whether they gave cash, but I heard of some other wedding which was there in somewhere in Singapore or China somewhere. The wedding couple, they gifted some around 90,000 in Indian currency to all their visitors. In like this in envelopes. I don't know, some strange culture thing. I thought when we go for weddings, we are supposed to give gifts, but some parallel universe where they give opposite. Finish copying. 75, 273, 50. The world has reached to a point where the boy has to pay the girl nowadays. Huh? See, in the olden days, the girls used to pay, what do you call that, dowry, right? For getting married. So now the things have gone so bad that boys have, in some parts of India, boys have to either kidnap a girl, okay, or they have to pay a dowry for the girl or something like that. This is a real thing in some parts of India, in Haryana and all, where the sex ratio is very bad. No, apparently some people didn't see this coming. It was obvious, no, if the girls become less, obviously the boys won't find an equal number of brides to get married. So it's become a situation where boys have to pay dowry. Okay. Okay, so what is this sample? Okay, so let us solve this one now. Wait, I think so there's a sub question further on. Okay, write this down also. Write this down also. Why there are three people sitting on one desk over there? Huh? There are so many desks empty over here. See, those girls are sitting one per desk over there, both of those two girls. And they are sitting three on a desk. Okay, finished? Yes. Right. Done? Okay, let's go then to solve the problem. Okay, so exercise 1. So what is going to be the sample space here? What are the possible, you buy one envelope, what are the possible values you'll get inside them? There is only given as what is the sample space? When you buy an envelope, you'll either get $100 inside it, or what is the next number? $25. And $10, right? Okay, so there are only three options in the sample space. Okay, so how many envelopes have $100 in them? So 75 envelopes have $100 in them. How many envelopes have 25? And how many have $10? 75. Okay. So now basically what should be the probability of getting 100 this thing? I'll write $100 so that's clear. So it's going to be 75 divided by 500. because there are total 500 envelopes, out of which 75 contain $100 in them. So what will be the probability of getting 25? And what will be the probability of getting $10? Okay, this is upon 500. Okay, this is done. What is the last part of the question? What is the probability that the first envelope purchased contains less than $100? So what we are asking for is probability of less than $100. Okay, but what are the numbers less than $100 over here? Its probability. So what is the situation when you have less than $100? Either you get $25 or you get $10, right? So what you'll write? Probability of $25 or $10. Okay. So now one thing over here is can you get $25 and $10 in the same envelope? No, right? That situation does not arise, right? So $25 and $10 are mutually exclusive. In other words, their intersection is empty. Okay, you cannot get $10 and $25 in the same envelope. Okay, so this will become probability of 25 plus probability of $10. So how much is this number? Tell me. 150 plus 275 upon 500. So this is equal to 425. Okay, so this is the final answer. Clear? Let's go to the next question. Right fast. Okay. So write down this. Suppose that in a senior college class of 500 students, it is found that 200 smoke, 210 smoke, 258 drink alcoholic beverage, 216 eat between meals. Uh, what do you mean by eat between meals over here? What do you mean by eat between meals, by the way? See, when they talk of meals, there are fixed timings of meals. There is the breakfast in the morning, you have lunch in the afternoon, and you have dinner in the evening for them. And this book is written in examples from America, and they have dinner at 6 o'clock in the evening. Yeah, they are pretty weird people if you know that. Like if you have watched some of this TV shows and all, like Young Sheldon and all, they're having dinner when it is still light outside. Okay, so it's kind of weird, but they have dinner at around 6 o'clock. Okay, and after that they have one more late night meal. So there are 4 meals for the day. So eating between meals is like you have something in between. Okay, like you eat some chips or something like in between time or something, or some snacks. Okay, it's kind of unhealthy, I suppose. That's what they're trying to mention here. Okay, so 216 of them they eat between meals, 122 of them they smoke and they drink alcoholic beverages. Not necessarily in that order, but they do it together. Okay, 83 eat between meals and drink alcoholic beverages. 97 smoke and they eat alcohol and they eat meals. And 52 of them they engage in all three of these bad health practices. Yeah, eating between meals is usually you're going to eat some junk food, like chips or something like that, right? Nothing else you can think of eating between meals, right? So this way it's counted as a bell head practice. Okay, let's note down the question. If a member of the senior class is selected at random, okay, if a member of the senior class is selected at random, find the probability that the student smokes but does not drink alcoholic beverages, eats between meals and drinks alcoholic beverages but does not smoke. Okay, neither smokes nor eats between meals. Okay, 3 questions are given. Hey, write fast one. There are at least 5 examples more. Wait, I'll just check. Six exercises are there. You're still on number 2. Fast. Write fast. Write fast. Then, okay, so we'll solve this thing. Okay, so let what are the three things which are given to the smoker, alcoholic, and eat between meals? Okay, instead of A, B, C, I'll use this alphabets. Let S be the event that the selected student is a smoker. Or rather, I'll say smokes. Because there's no place here. They have not mentioned what he smokes, so you have to be a little neutral here. Okay. What else was there? Let A be the this thing that he drinks. The spelling is wrong, but I don't have place to adjust it. Okay, and let M be the event that the selected student eats between meals. Okay, so now next what we'll do is how many students are given to us in total? Oh, wait, I kept S for this, no, but S we also require for the sample space, no. So what we'll do now? We have to change this alphabet. What we'll put? Why R? How do you describe a smoker? Q is better, no? See Q. Okay, let Q be the event that the selected student is a smoker. Okay, so now what is given to you is and S be the sample space, huh? All students. Okay, so now number of people in the sample space are how many? How many are there in the class? 500, right? Yeah, so there are 500 students in the class, but this actually means that the batch is of 500 students. This students actually get divided between the subject and all later. It's a very rare case that one teacher is going and teaching 500 students in one go. Okay. Like in bits, and I think so in some of these engineering colleges, their classes are as big as 150 to 200, like that. I don't know in GC how big classes they have, but some of these colleges do have 100, 200 students in one class. But after that it splits. If they have 300 students, then 100 in one division, the remaining 200 in the other division, like that. Okay. So number of people in Q. How many are given? How many smokers are there? 210. How many alcoholic people are there? 258. How many eating between meals are there? 216, right? Okay. So next now, how many people are there in between this now? How many people are smokers and drink alcohol? Just check and tell me. Smokers and drink alcohol. 122. Then smokers and eat between meals. 97. Then what remains? Alcoholic and eat between meals. How much is this? 83. And then what remains is how many of them are all three of them? Okay. I'll solve this problem in detail, but for the subsequent problems we'll take shortcuts, so we won't write all these details and all. Okay? Huh? Yeah, we have 6 problems to solve. Oh, yes. So what goes if you don't eat food for one day?
Usually we have a lunch break at 1.
Why?
Disturbing things like
No, I said you should not eat between meals. I know. You all don't even have a? Why you don't have breakfast?
There's no time. Then you break. Yeah, you have break also.
I'll come to your house, cook breakfast and come. Huh? Where you stay? I thought I'll come to your house and eat breakfast over there. One thing I realized when my mother was not at home and when I had to cook breakfast, it takes 1 hour to cook breakfast for me and 15 minutes to eat it. No, it takes more time to cook it than to eat it. That is bad. Yeah. Actually, no, they should start canteens in buses. That can help us save in time. Well, can yeah, she got a startup idea. But there's no time to stop at the bus stand. No, the canteen should be inside the bus. Like how they have. That thing what you're calling, no? That thing with a bed, a washroom and all, it's called a train. Okay. Some of this, some of these interstate buses, they have washrooms on them and they have wash basin and all. They have a bed also in them, but only canteen is missing. So we'll try to do some changes in those buses. We'll tell Kadamba. Okay. Yeah. See, I'm being so generous to you all. I'm not describing examples containing food and all. My previous batches know when I used to teach in Chogles and I used to teach this paper mostly, the examples were about pizzas, french fries and all. See, I'm not discussing food also here. Okay. So, okay. So let us now calculate the. What is the question here? First thing, probability. The first one is probability he is a smoker but does not drink alcoholic beverages. He is a smoker but does not drink alcoholic beverages. So A complement. Okay, what should be this? Okay, before we go to this example, no, just write these things over there. Some variations of the results which I've already given you all. What is going to be probability of A complement, by the way? We have already seen a thing that which says the probability of A plus probability of A complement is equal to 1. So what should be probability of A complement? Huh? Yeah, so how you count it? We had said probability of A plus probability of A complement is equal to 1. So what should be this? 1 minus probability of A, right? Clear? Okay, this thing you all keep in mind. Another thing you all have to keep in mind is I had told you all that probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Okay, so in this case, what should be probability of A intersection B? What should this be? Easy question, man. Just rearrange the terms, no? This will become probability of A plus probability of B minus probability of A union B. Circle. There is nothing on top. There, sideways it is. Yeah, this is this side, no? Okay, so this is the starting part. Done? Right, wrote down.
This.
You said, sir, wait. I don't know, we'll finish the problem. It's not good to keep things incomplete in life. Okay, what should this be according to the formula which I just wrote down over there? This should be probability of Q plus probability of A complement minus probability of Q union A complement. Okay? Okay, so हम right, this is just going by the formula. Wait, I'll write one more step. I'll write one more step, otherwise it will become a confusion. This is probability of Q so this will be number of people in Q minus upon number of people in the full sample space. This will be 1 minus number of people in okay. Yeah, so this numbers, first two numbers are known to us. I think so. Number of smokers is 210, right? This will be 1 minus number of alcoholic people is alcoholic people are very 258. And this is 500. Huh? No, actually this next thing requires calculation, so I think so we'll stop here. Otherwise we'll have to go to the diagram and all. So we'll continue with this problem on Friday morning at 9:30. Come on without fear. You'll be actually feeding a milk to a real snake. Not a real snake, it's a real nag. Okay.